So I want to start off by talking a little bit about the geologic history and the geologic processes that we see along Puget Sound coastlines. It's useful to understand the way shorelines work now to have a sense for where they came from. And shorelines are a dynamic geologic area, so it's useful to kind of understand what sorts of geological processes are acting um, in real time here. So let's start off by looking at a little bit of the history of Puget Sound. And we're just going to go back about 14,000 years, a little further than that actually, but back to the last glacial advance. The This outline shows the extent of the Vashon Lobe of the Cordilleran ice sheet, which reached maximum about 14,000 years ago. It advanced from the coast mountains of British Columbia, advanced down through into Puget Sound, and when it spanned the distance from the Olympic Mountains to the Cascade Mountains, it cut off all of the saltwater access to Puget Sound. And in front of the glacier as it advanced was actually a big freshwater lake that drained out through the Chehalis River. Actually, that was and so as the glacier advanced, it was actually advancing into that freshwater lake. Around the city of Seattle, the ice was about 1 kilometer thick. So this drawing's roughly to scale. And if you imagine that thickness of ice, that massive ice sliding over the landscape, you may get some kind of sense for the amount of kind of work that ice sheet performed. And much of what we see in Puget Sound today is a result of that glacial advance. And we normally think of glaciers as being kind of pure, pristine, aquamarine. In fact, they're so clean we want to drink them. But the reality is actually a little bit different. At the upper part of a glacier, they're very erosive and they're grinding up rock and picking up sediment. That sediment's sort of carried in a one-way conveyor belt down to the toe of the glacier, which is where we are in Puget Sound. And so the toe of the glacier as it advanced was probably filthy. This is an example of a glacier in Alaska, but the toe of the Vashon Lobe probably looked very much like this. So it was carrying sediment both within the ice and in meltwater streams underneath. It was discharging that sediment both in these fine sediment and these meltwater streams and coarser sediment, sand and gravel. It was deposited right in front of the glacier as it advanced. This is kind of a picture of what that advance might have looked like in cross section. So here we see the ice lobe. There's a layer of what's called glacial till that's deposited right at the base of the ice as it slides over the landscape. And then there's this big thick wedge of outwash deposits. So this is the sand and the gravel that we saw in that Alaska picture. And the ice is advancing over that. Here's the lake that's out in front. So the fine sediment that's carried in meltwater streams is deposited on the bottom of the lake. And all of this kind of package of sediment advances to the south, and it's all deposited over the sediments that were here prior to the glacial advance. And if we kind of think about that whole package of sediments, we might see something like this. So this is kind of a typical beach bluff in the Puget Sound. At the bottom, you might have pre-glacial sediments. Then you might have those lake sediments from the freshwater lake, and then often a thick unit of advanced sandy, gravelly outwash here, and a relatively thin cap of glacial till. And then often kind of scattered in a irregular pattern on top of that, you may have recessional outwash, which was stuff that was deposited as the glacier was receding. And we can actually see those units in a lot of areas around Puget Sound. This is in West Seattle, Fort Lawton. And if we look at this, we see this kind of tannish layer at the bottom. That was the pre-glacial sediments. We see this gray layer here, lake sediments, and you'll notice that there's a lot of evidence of instability there and seepage coming out on top of that. That's real characteristic. And then a thick layer of this kind of grayish tan outwash. And we can't quite see it in this picture, but right at the top of the bluff, there's a layer of glacial till. This is often called hard pan by builders and homeowners. And one of the critical things to understand is that as a result of that glacial history, our beach bluffs are stack of different layers of sediment, coarse sediment and fine sediment, and that stratification has really serious consequences in terms of how the bluffs act, and we'll talk about that a little bit later. So we looked at the glacial sediments in cross section. Let's see what Puget Sound looks like in plan view or from above. If you look at this shaded relief map of the Puget lowland, just if you back up, you really see two basic kind of landforms here. First of all, you see the upland areas, which are mostly in this kind of green tint here. And even casual observation, you can see this really pronounced striation that covers virtually all of that land surface. And that is directly the impact of the glacier sliding over the ground surface as it advanced to the south. And you can see that, you know, virtually every upland surface here shows some evidence of that glacial advance. And then the other feature that's quite prominent is kind of dissecting that glacial upland are a whole series of these kind of deep troughs. So, you know, we have Puget Sound here, Colvos Passage, the main stem of Puget Sound, and then even Lake Washington, Lake Sammamish, and over to the Sammamish Valley. These are also thought to be glacial features, and the current thinking is that these were actually evacuated by glacial meltwater that was flowing underneath the glacier. Water is heavier than ice, so as the glacier was melting and as precipitation was falling on it, it would seep through the ice down to the bottom, and then it would flow as a meltwater stream under pressure, actually, between the ice and the ground surface. And you can imagine that that might have been a very effective way of eroding the soil underneath the ground surface, and that's as a result we see these deep troughs. And so here's just a cartoon, a cross section of what it might have looked like across Puget Sound when the glacier was at its maximum. And here we see this upland area kind of striated by the glacial movement. We have the meltwater stream that's scouring this meltwater channel. And if we remove the ice, here's what was left when the glacier retreated. We still have this upland surface, and now saltwater has re-entered the basin, and so we have a saltwater body that's occupying Puget Sound now. It's interesting that for much of this land surface, really not much has happened since the glaciers left. On this upland surface, you could see in that shaded relief image how pristine that looked. In the bottom of Puget Sound, fine sediment is gradually accumulating, but very slowly. The place where we see a lot of action happening is at the coastline here, where the water surface of Puget Sound intersects that glacial bluff. So we have this really kind of characteristic check mark in the landscape that's composed of a wave-cut bench here, and then the corresponding bluff that's behind it. And it's this sort of check mark in the landscape that we're really going to be talking about for most of the rest of the day here. And you can see those features here. Again, we're in West Seattle. So you can see those features. This is that upland area, really pretty much unmodified, except for building houses and roads on it. And then here's the bluff, the back of that checkmark feature. Here's the wave cut bench, upper parts of the beach that extends out here. And then further out, we have deep water. So let's start off by talking about the processes that are going on beach bluffs. And one of the first things to recognize about coastal bluffs here in the Puget Sound is that they are inherently unstable, and virtually all coastal bluffs are retreating at some rate over a long period of time. This was a study that was done back in 2018, and they looked at 185 sites around Puget Sound and places where they could find landmarks or references that allowed them to measure the long-term rate of bluff retreat. And there's a couple intriguing things about this graph, and probably the most interesting is looking at how few of those bluffs didn't show any retreat at all. In other words, the vast majority of bluffs that they looked at showed some level of retreat, with an average of about a third of a foot per year. And of course, that retreat doesn't happen, gradually a little bit every year. Typically, nothing will happen to a bluff, and then there'll be some kind of large event that might happen once every 10 or 20 or 30 years. So let's take a look at how that bluff retreats, what happens over time. And it retreats in a couple of different ways. There's different processes that erode the bluff. One of them is what we call single grain erosion. And that's basically, think of that as kind of the bluff wearing away. So that happens where there's very dense, hard glacial sediment right at the beach face. This is glacial till. And this is probably the slowest mechanism of bluff retreat. So bluff is retreating, but not quickly. Bluffs can be eroded by flowing water. So if there's water flowing over the bluff, it has a lot of erosive energy. And in fact, it has so much erosive energy that where that happened naturally, where streams flowed over the bluff immediately post-glacial, the bluff in those cases has actually almost been removed in every case, and there's a valley or a gorge that extends all the way down to beach level. But the place where we see this kind of erosion frequently is where people are discharging surface water over the face of the bluff. And we'll talk about that a bit more later this morning. But the main way that bluffs retreat is by some form of landsliding. There was a relatively recent paper that was done by a gentleman up at the University of British Columbia who looked at and identified 36 different types of landsliding that occurred, and considered the possibility of discussing all 36 of those this morning. But I was persuaded that perhaps it made more sense to trim that down a little bit. So what I'd like to do is just talk about two general types of landslides that are common around the Puget lowland. And the first one I want to talk about are what I would characterize as shallow landslides. These are by far the most common type of landslide on coastal bluffs. And this is what happens when you have a relatively shallow layer of soil, as you can see here, often with a vegetated cover. And that whole layer of soil becomes saturated and slides off, kind of like a carpet on a linoleum floor. That mass slides to the base of the bluff and exposes the bluff face, which gradually accumulates additional soil over time. These kind of shallow failures are often driven largely by surface water draining over the bluff, by precipitation directly on the bluff. They can have some influence too by seepage emerging from the bluff. We were lucky enough actually to have a video of one of these small slides. So that was a pretty dramatic video. And I think it shows, and that was actually quite a small landslide. It was maybe 20 feet long, 20 feet deep, and a few feet thick. But it gives you some idea of the power of even that small mass of soil sliding to the base of slope. And even though these slides are small, and they're often kind of a nuisance, they close roads or close the railroad tracks. They can be deadly if you're in the wrong place. On Bainbridge Island back in 1996, a relatively small slide here directly impacted a house that was built on the beach, and a family of 4 was killed in that accident. One other type of shallow slide that you'll see, particularly where beaches where bluffs are eroding very rapidly, are slab failures or topple failures, where a chunk of the slope, chunk of the bluff becomes detached and kind of slides to the bottom intact. And that's the sort of slide you see here. And it's really characteristic just of where bluffs are eroding really quickly. So that was kind of a brief discussion of shallow landslides. The other type of landslide I want to talk about are deep-seated landslides. So whereas a shallow landslide may be a few feet thick, one of these deep-seated landslides may be 50 or 100 feet deep at the deepest point. and they're characterized by kind of rotational movement here. These deep-seated slides are driven almost entirely by seepage, by deep groundwater emerging in the slide area. So whereas shallow landslides are often triggered by an intense rainstorm event, typically movement on a deep-seated landslide occurs after, say, a whole season of above average rainfall. And here's just a cartoon that shows what one of these landslides might look like. So here we see a hillside. It's raining. Hillside's getting saturated, and then it fails. And you see this characteristic rotational movement where the upper part of the slide goes down and the toe of the slide actually may come up. And it leaves this very characteristic form on the landscape. And we see that kind of topography in many places on Puget Sound. This is the south end of Vashon Island. And here you can see a landslide topography from an old landslide. Here's that upper slide scarp, this kind of rumpled topography down here. And in this case, the toe was probably emerged out on the beach and was eroded away. Now, a little bit of a wrong impression that I may have given you. The cartoon that we looked at showed that failure occurring on a slope that was previously undisturbed. And that's actually very uncommon. We don't see very many of those. We see a lot of these kind of features that represent old landslides that have failed in the past. And the concern that we have with those is that often, or in many cases, sort of periodically, these masses may become saturated and start to move again. So this is a famous example of that. This is Perkins Lane in Seattle. Many of you may have heard of that. That was a whole neighborhood that was built on one of these slide blocks. And over a long period of times, it's moved periodically, including this really catastrophic movement in 1996. And another example, and perhaps a more typical example of what might happen on one of these old landslides, this was a development that was built on Carlton Beach in Thurston County. The presence of the landslide wasn't recognized when the neighborhood was built. Been there for a number of years, and then in a wet year, people started noticing cracks in the sidewalk, foundation cracking, buildings being distorted. These kind of landslides seldom represent a risk to public of life or safety, but they can gradually just destroy the infrastructure and buildings that are located on them. In this case, some number, I think maybe 10 residences were completely destroyed. And a sobering aspect of that is if you look closely at your homeowner's insurance, typically homeowner's insurance doesn't cover damage from landslides. So these unfortunate folks, the only relief that they received through this whole incident was that they were able to take the debris from the landslide to the Thurston County landfill for free. So that was just a kind of a brief discussion of the processes that lead to this gradual erosion or retreat of coastal bluffs. Now let's go to the other part of that check mark. Let's look at the wave cut bench and the beach processes that are occurring there. So here's a typical kind of Puget Sound beach, often with an area of fine sediment and the low tide terrace, and then a zone of coarser gravelly or cobbly sediment on the upper beach. And if we want to think about how beaches form, we want to recognize that they are virtually entirely a product of wave impact on the shore. If it wasn't for waves, we wouldn't have beaches. And most waves, of course, are formed by transfer of energy from wind blowing across the water surface and moving the water surface, creating water waves. The stronger the wind and the longer the area that the wind blows, the larger the waves become. And if we look at what happens to waves in the deep ocean, you can see these particles of red represent water particles. And as the wave goes by, the particles move in a roughly circular motion. But after the wave passes, the water ends up in the same place where it started. So the wave is transmitting energy, but it's not moving water out in deep water. But that circumstance changes as the beach approaches shore. As the beach comes into the shore, when the water reaches a depth of about half the wavelength of the waves, this circular movement that you saw starts to interact with the bottom. And as that happens, it actually slows the wave down. And as the wave slows, it's got the same amount of energy, so it gets taller. And the top of the wave is, again, following that circular motion, is actually moving forward. And eventually the wave breaks. And the circumstances change when the wave breaks. In the open ocean, the wave is not moving water at all. But as the wave breaks, it's actually throwing water up onto the beach. So it's actually transporting water onto the beach. And we have a quick video here that shows kind of some important aspects of that. So this is just a small wave breaking on the beach here. Let's see. Here we go. So there's a wave coming in. As it steepens, it approaches the beach. And here we have it breaking. And as it breaks, you'll notice that that mass of water is being thrown up towards us on the beach here. And you can see the energy that's implied by that by the foam in that water. And then as the wave, and you notice that kind of nice white color mixture of foam and air and water there. And then as the wave continues, all of a sudden, boom, the color of the wave changes. This wave has just picked up a lot of sediment from the beach face. And now as the wave moves, it's going to carry that sediment up onto the beach. Carries it all the way up until that energy is dissipated. And at the high point of the swash, it's carried sediment up onto the beach. And then the swash drains back down, back towards the water. Now, as the swash drains down, it doesn't have nearly as much energy as the wave coming in, but it's going downhill. And so on a beach that's stable, the energy of the waves moving sediment onto the beach is just balanced by the ability of swash to move them down. And so that process continues. The sediment's continually in motion, but there's no change in the beach profile. All right. So we saw in that last video sediment moving up and down the beach in response to wave movement. But waves typically don't impinge on the coastline parallel to the beach. They often come in at an angle. So that has some significant consequences. And if we imagine a wave coming into the beach here, wind and waves are coming from this direction, and this is a particle of sand on the beach. And as a wave comes in, it carries that particle of sand diagonally up the beach. But then when the swash drains down, it moves that particle of sand straight down, kind of the fall line of the beach. And as that process is continued over time, the particle of sediment is going to move in this kind of zigzag pattern along the beach. And in this case, it's moving from left to right. And that process of sediment movement is called longshore drift. So that's kind of a gradual movement of sediment along the beach driven by wave action. And if we look at what that happens on a larger scale, you have some characteristic beach forms that are a result of that. So in some cases, you have what's called a diversion point here, where wind energy is just balanced. And so some sediments going this way, some sediments going this way. There's no sediment supply to this point. So the beach here is often coarse, and the bluff is often subject to rapid erosion there. And then sediment moves along the beach. And if you look at this sediment is moving from left to right. This sediment's moving from right to left. It moves along the beach until it meets another beach where the sediment's moving in the same direction. And when those two, when the drift self, when the movement of sediment along the beach meets, what you have is some kind of an accretional shore form, which is often takes the form of a spit. Now, if we look at actual beaches in the field, we can see evidence of the sediment movement. So here's a beach, and you can see that sediment is moving away from us. It piles up on the up drift side of this log, moves around the log and continues down here. There's a deficit on this side, so we can see here evidence that sediment is moving away from us, or in this case, from right to left. looking from the water side. Now, the direction of sediment movement varies through the year because storms come in from different directions, but typically over the course of the year, there will be a stronger, a dominant wave direction. And for most of Puget Sound, our big storms come from the south, and so the direction of sediment movement tends to be to the north. So you can see that here on Vashon Island. The green line here represents sediment movement from left to right. So sediment's moving along Maury Island here. And the kind of rust-colored line is sediment moving from right to left. So moving again north along the shore of Vashon. But in places where the beach is protected from south winds, so for example, here on the north shore of Moray, we obviously no impingement by waves from the south. So the primary wind and wave energy is from the north, and so sediment here is moving in that direction. So now, if we look at what some of those features might look like, here's a diversion point. Sediment's moving both directions. Coarse sediment on the beach and probably rapid erosion of the bluff. As we move down the beach, you have continued contribution of sediment from bluff erosion. And then you may also have sediment that is contributed by streams that are flowing out onto the beach. And then you move down far enough, you end up with a place where two drift cells come together and you form an accretional shore form like this. The entire shoreline, actually all of the marine shorelines of Washington State have been mapped. This is an example of that map. This is available from the Washington State Coastal Shoreline Atlas. So if you're interested, you can look at your shoreline and see what the direction of shoreline movement is in your neighborhood. One of the complete sets of shoreline movement here, starting at this diversion point with the transport zone and the accumulation, is called a drift cell. So this entire feature is a drift cell, and this is an entire drift cell here. So it's useful as you're thinking about your beach and beach processes to have a sense for what your drift cell is, where sediment's coming from and where it's going. In many beaches throughout the world, this is Cape Cod, for example, that movement of sediment along the beach is the only process by which the beach forms. So the coastal islands off the East Coast are entirely a result of this kind of littoral or longshore drift. But that's actually not true here in Puget Sound. Because of our young topography here, our youthful geologic setting, we have a more complex beach process here. So here's again a typical Puget Sound beach with fine sediment here, coarser sediment up here. This fine sediment may well move during every tide cycle. Small waves can mobilize this, so this may be actively moving. The coarser sediment up here may be moving much more slowly. Maybe it's only mobilized during relatively large storm events. And then often on Puget Sound beaches, we have these large boulders that may seem a little out of place. And those are actually a result of the retreat of the bluff. And when a boulder is encountered in the bluff, if it's too large to be moved, it just falls onto the beach face and stays there. So where you see these large boulders scattered on the beach, that's direct evidence of the fact that the bluff used to be there and it's retreated from that point.